Applications of Iterative Methods. Iterative methods are useful in many fields of science, but they are particularly important in geometry, where we often deal with measurements. Thus we often encounter situations where the quantities measured are irrational, because there may be an irrational constant such as Archimedes' constant pi involved in the calculations of the area of a circle, the volume of a sphere, etc. Let's explain this point through an example. Example 1. A sphere was immersed in water and as a result, the volume of water increased by 3,140 centimeters cubed. Use iterations methods to calculate the radius of this sphere in cm. Let's assume that your calculator is of a basic type and includes only the 4 basic operations: addition, subtraction, multiplication, and division. Express your answer to 1 decimal place. Use the formula for calculating the volume of a sphere. V equals 4 over 3 pi r cubed, where pi approximately equals to 3.14. Solution 1. The volume of the sphere is equal to the volume of the displaced water, as the sphere now occupies the space which was previously occupied by water. Hence, we have V, water equals V, sphere equals V. We have the following as shown on screen. We have the following as shown on screen. Now, we have to identify an interval that includes the value of the sphere's radius. It is easy to find that this interval extends from 9 cm to 10 cm, as 9 cm cubed equals 9 cm times 9 cm times 9 cm equals 729 cm cubed, and 10 cm cubed equals 10 cm times 10 cm times 10 cm equals 1000 cm cubed. Therefore, it is evident that the radius of our sphere is between 9 cm and 10 cm. Using the half interval iteration method, we obtain x equals 9.5 cm. We have the following as shown on screen. It is clear that the radius is between 9.0 cm and 9.5 cm, as 750 is between 729 and 857.4. Solving again for the half of the new interval, i.e. for x equals 9.25 cm, we have the following as shown on screen. This means the radius is between 9.0 cm and 9.25 cm, as 750 is between 729 and 857.4. Hence, taking the new half interval as x equals 9.125 cm, we obtain the following shown on screen. Therefore, the result is between 9.0 cm and 9.125 cm, as 750 is between 729 and 759.8. Hence, since we want to express the result in 1 decimal place, we write r equals 9.1 cm. Now, let's consider another example about the use of iterative methods in geometry, but this time involving the area of figures. Example 2. A rectangle has an area of 200 cm squared. One of the sides is 9 cm longer than the other. A. Find a suitable equation that gives the rectangle's area in terms of its sides. B. Identify the 1-unit range between 2 integers where the shortest side takes the value. C. Find the lengths of each side expressed in 1 decimal place. D. Estimate the error made when using such methods of approximation by calculating again the area of the rectangle, this time using the dimensions found in Solution 2. A. We can denote the smallest side by a letter, for example, x. Therefore, the longest side is x plus 9, where both x and x plus 9 are expressed in centimeters. We have the following shown on screen. Since the area of a rectangle is calculated by multiplying its dimensions, we have the relation. We have the following shown on screen. For the area of our rectangle. Thus, since A equals 200 centimeters squared, The equation expressing the sides of this rectangle is shown in the following on screen. This is a quadratic equation that cannot be factorized, as we did in tutorial 6.4. Therefore, we must try other methods to find the value of x, b. We make a quick mental calculation to identify the possible range of the two consecutive integers where the value of x may be. Thus, taking x equals 10 yields, we have the following shown on screen. Hence, 10 is the lower bound of the interval, as explained in tutorial 2.2. The next value, therefore, the one that represents the upper bound, must be bigger. Taking x equals 11 yields, we have the following shown on screen. Therefore, now we are sure that the smaller side x is greater than 10 and smaller than 11. Since we are not able to find an exact value for x, it is necessary to use iterative methods to find its approximate value to one decimal place. It is better to use the half interval division method instead of the going through values in order method, as since we want the result expressed to one decimal place, the half interval method does not require more than 3 to 4 steps in all. Thus, since half interval between 10 and 11 corresponds to 10.5, we have the following as shown on screen. This means the result is in the lower part of the interval, i.e. between 10 and 10.5. Thus, for x equals 10.25, halfway between 10 and 10.5, we have the following as shown on screen. Hence, x lies between 10.25 and 10.5, values that give opposite signs. Taking again halfway between these two values, i.e. x equals 10.375, yields, we have the following as shown on screen. This means the result lies between 10.25 and 10.375. When rounding it to one decimal place, we obtain x equals 10.3 centimeters. In this way, we found the length of the shorter side, width, w. The value of the longest side, length, l. Therefore is x plus 9 is equal to 10.3 centimeters plus 9 centimeters equals 19.3 centimeters d. Now, let's calculate the rectangle's area using the dimensions we just found. Thus we have the following shown on screen. This value is very close to the original one. The error is only 200 centimeters squared minus 198.79 centimeters squared equals 1.21 centimeters squared. However, this error would be much smaller if we increased the accuracy of dimensions calculation to 2 decimal places or more. This means the result would be much closer to the original value, 200 centimeters squared. That is all for lesson 9.4.2. To continue this tutorial, please watch 9.4.3, exercises involving iteration. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.info.